The purpose of this lab was to utilize Newton's second law in order to examine an object in constant motion and to create a computational model to predict its motion and compare it with the real-world results. One could also utilize the position update formula to create a position versus time graph to predict the future position of the ball. Newton's second law states that the net force of an object equals its mass times its acceleration, and one can arrive at a form of Newton's second law that allows one to predict the final velocity of the ball and the final location of the ball at a certain time after the initial motion has occurred. The first step was to utilize Tracker in order to analyze the motion of a soccer ball rolling across the top of a table. One of the problems encountered was that Tracker imported the video upside down. This is not a major issue because the physics of the ball were the same. There was no net force in the horizontal direction being applied to the ball while in motion, so the only thing that needed to be accounted for was the direction in which the ball was traveling. The magnitude remained the same. In order to get the best analysis possible, the video started analyzing the ball's motion shortly after the ball had been in constant motion for a certain reasonable amount of time. The origin of the system was defined at the center of the soccer ball during the first frame of the video, which represented time equaling 0. The axes were the same as our Cartesian coordinate system, with the ball traveling in the negative x direction. In order to calibrate the software properly, the diameter of the ball was set to 0.22 meters. During the analysis of the video, position versus time graph was being analyzed and eventually compared to the data produced by the computational model. The next step was to create a computational model of the ball's motion using VPython. First, the ball's mass was defined as 0.45 kilograms, and the ball's initial position was defined at the ball's starting point in the video. Given that the video was analyzed upside down because of technical issues, the same physics had to be applied to the model. The only modification that needed to be made was that the initial velocity had to be initialized in the negative direction. The magnitude remained constant. In order to define the initial velocity of the ball, however, two time frames needed to be chosen in order to calculate the difference in position. Then, that difference in position was divided by the time difference between the two frames, which in this case was 0.33 seconds. The initial velocity was calculated to be negative 1.3 meters per second. The program ran a while loop that looped through a time interval of 1 second and applied both Newton's second law and the position update formula for each iteration. Overall, the computational model predicted the real-world model with a high degree of accuracy. There were some experimental errors that unfortunately kept the experiment from attaining the best possible data it could have produced. One of these problems was friction. The total net force on the ball wasn't exactly 0, but somewhat negative because of friction, which is not taken into account in the computational model. Next, there was some slight vertical motion of the ball, which could have produced some errors within the data. The last error was placement in the center of the ball in each frame of Tracker. There were certain times in which the center was not completely accurate or consistent, which could have also produced flawed data. Now here are some questions to be addressed. What if the axes were switched? If the axes were switched, then the direction would change and the sign of the velocity vector would change signs. Is it possible to define the amount of pushes and pulls on the object to produce a net force of 0 in the case observed? It's not possible because theoretically there could be an infinite amount of forces on an object. Given this condition, one cannot accurately state how many are acting on the ball in total.